In today's video, I'm going to be talking through the AQA GCSE Physics Paper 1 for single science candidates, and it's from May 2018. 1. Figure 1 shows a student walking on a carpet. The student becomes negatively charged because of the friction between his socks and the carpet. Explain why the friction causes the student to become charged. This answer is always the same. It's to do with static electricity, and it's basically due to the transfer of electrons. And say, because it's worth 2 marks, which direction that occurs in, and that is from the carpet to the student, because the student becomes negatively charged. And I'm going to change my tip because I think it's a bit too fat. 1.2. The student's head is represented by the sphere in figure 2. The student is negatively charged. The arrow chart shows part of the electric field around the student's head. Draw 3 more arrows on figure 2 to complete the electric field pattern. Handily, they've already shown you the direction and where it occurs, so where would 3 more arrows fit nicely? Well, here, here, here and here. The negatively charged student touches a metal tap and receives an electric shock. Explain why. So first of all, you need to point out that there is a buildup of charge or potential difference between the student and the tap. And then similar to the previous question, so what's going to happen is effectively those excess electrons are going to jump from the student to the metal tap. So we need to say that the electrons, so just like the previous question, transfer themselves from the student to the tap in order to earth themselves and remove excess charge. (1.4) Some carpets have thin copper wires running through them. The student is less likely to receive an electric shock after walking on this type of carpet. Suggest why. 2 marks. The key here is that there's copper running through the carpets. So carpets tend to contain plastic or wool, so those are electrical insulators. The moment you add the copper wires, then you add an electrical conductor. And therefore you don't get any buildup of charge. So copper is a good electrical conductor. So you get no build-up of electrical charge. A teacher used a Geiger-Müller tube and counter to measure the number of counts in 60 seconds for a radioactive rock. The counter recorded 819 counts in 60 seconds. The background radiation count rate was 0.3 counts per second. Calculate the count rate for the rock. So in order to do this, we need to subtract the background radiation from the real reading. So we need to work out the amount of background radiation that occurred. So I'm going to say I need to work out the amount of background radiation that occurred in 60 seconds. So I'm going to do 0.30 times 60 to work out that there were 18 counts in 60 seconds. So to work out the real reading, we need to take out that background radiation from the reading in 60 seconds to get 801 counts in 60 seconds. And then because we need it per second, we just take that number and divide it by 60. And once you've done that, you get 13.35. 2.2. A householder is worried about the radiation emitted by the granite worktop in his kitchen. 1 kilogram of granite has an activity of 1,250 becquerels. The kitchen worktop has a mass of 180 kilograms. Calculate the activity of the kitchen worktop in becquerels. So we just need to take that 1,250 becquerels and multiply it by the mass. And then once you've done that, you get this huge number. The average total radiation dose per year in the UK is 2 millisieverts. Table 1 shows the effects of radiation dose on the human body. So we've got our radiation dose, 10,000 causes immediate illness, death within a few weeks. 1,000 causes radiation sickness and is unlikely to cause death. 100 is the lowest dose with evidence of causing cancer. The average radiation dose from the granite worktop is 0.003 millisieverts per day. Explain why the householder should not be concerned about his yearly radiation dose from the granite worktop. Notice that 1 year is 365 days. So let's work out the dose over a year. So we take the amount per day, which is 0.003, then we multiply it by the number of days in a year. And then once you've done that, you get a value which is 1.095. Now 1.095 is far less than the 100 millisieverts, which causes cancer. So that dose is so low that we're not going to have any issues here. Bananas are a source of background radiation. Some people think that the unit of radiation dose should be changed from sieverts to banana equivalent dose. Suggests one reason why the banana equivalent dose may help the public be more aware of radiation risks. And any sensible answer here, but basically the fact that they're able to compare radiation risk with something every day, such as a banana, means that they'd be more likely to be aware. So people are able to compare a radiation risk more easily using the banana equivalent dose. Three, a student investigate how the resistance of a piece of nichrome wire varies with length. Figure 3 shows part of the circuit that the student used. So this is our battery. We've got an open switch here. This is a variable resistor. And then we've got the wire beneath. Complete figure 3 by adding an ammeter and voltmeter. Use the correct circuit symbols. So ammeter is fairly straightforward because it goes in series anywhere in the circuit. So I'm just going to pop it here. Now the voltmeter must be added in parallel, and let's work out where it needs to go. So the student investigated how the resistance of a piece of nichrome wire varies with length. So it's really the wire we're interested in. So that's why it has to go in parallel down here. 3.2. Describe how the student would obtain the data needed for the investigation. Your answers should include a risk assessment for one hazard in the investigation, and that's worth 6 marks. So if we scroll back up, we're interested in how the resistance of a piece of wire varies with length. So what are they changing? The independent variable. So the thing they're changing is the length of wire, e.g. 2 centimeters, 4 centimeters, 6 centimeters, etc. Now, in order to measure the resistance, you can't just add a device used to measure resistance. You need to use a different equation. So we're going to measure the current using an ammeter and the voltage or potential difference using a voltmeter, and substitute these values into the following equations, which is resistance equals voltage divided by current. Once you've done that, you can plot a graph. They love plotting graphs in physics of resistance against length. So we've said lots of methodology marks. Now let's look at a hazard. Well, it will probably get quite hot as the resistance increases. So that could cause the wire to melt. So as current increases, the wire could melt. and cause burns. So to prevent this, we want to use low currents, but don't worry too much. We've said hundreds of marks here, really. Why would switching off the circuit between readings have improved the accuracy of the student's investigation? So accuracy is all to do with how correct it is. The charge flow through the wire would not change. That's not true. The potential difference of the battery would not increase. I don't really like that answer. The power output of the battery would not increase. Again, irrelevant. The temperature of the wire would not change. Yes, you want to turn it off because when the current flows, it increases the temperature of the wire. So if you turn off the circuit, then you're going to help maintain that temperature. 3.4. The student used crocodile clips to make connections to the wire. They could have used a piece of equipment called a jockey. Figure 4 shows a crocodile clip and a jockey in contact with the wire. So the first thing I'm noticing is how much narrower that jockey is compared with the crocodile clip. How would using the jockey have affected the accuracy and resolution of the student's results compared to using the crocodile clip? The accuracy of the student's results would be higher. Yes, because it wouldn't be kind of obstructing so much of that ruler, so that would be true. The accuracy of the student's results would be lower. No, definitely not. The jockey would definitely be an improvement. The accuracy of the student's results would be the same. No, not correct. The resolution of the length measurement would be higher. Yeah, because you can see the finer increments on the ruler, so that's true. The resolution of the length measurement would be lower. No, not true. The resolution of the length measurement would be the same. Again, untrue. 4. Figure 5 shows a cyclist riding along a straight level road at constant speed. Complete the sentences. As the cyclist rides along the road, the something energy store in the cyclist's body decreases. Crucially, it's stored within his body, which means it must be chemical energy. The speed of the cyclist is constant when the work done by the cyclist is something the work done against air resistance. Okay, that value is just equal to. Figure 6 shows how the speed changes as the power output of the cyclist changes. Write down the equation that links power, time and work done. So in this space here, I'm going to write this formula triangle. I've always used we play tennis to help me remember it. I know that's weird, but it works for me. So I can see therefore that power is work done divided by time. Calculate the work done by the cyclist when his power output is 200 watts for 1,800 seconds. So work done is given by power times time according to that formula triangle. Power is 200 watts, time is 1,800. Pop it into your calculator to get 360,000 joules. Calculate the percentage increase in speed of the cyclist when the power output changes from 200 watts to 300 watts. Be careful, we need to use this up here to help us because we don't have enough information otherwise. So we're going from 200 watts to 300 watts. So we need to read across extremely carefully along here to get 9.5 as the lower value, and then up here we have 11. So to work out the percentage increase, we do change over original times by 100. And so let's do that. The change, well, what's the difference between 11 and 9.5? Well, that's 1.5. It's the percentage increase. So what was the beginning speed? 9.5. And then you want to multiply that by 100 to get a value which is 15.8. The maximum speed this cyclist can travel on a level road is 14 meters per second. How does cycling uphill affect the maximum speed of the cyclist? Explain your answer. So hopefully it's obvious to you that if he's going to go uphill, it's going to be more difficult. So therefore the maximum speed will decrease. And that's because the cyclist's maximum, I've written shorthand there, sorry. Power output remains the same, but the work done is carried out against an increased gradient. (5.1) Complete the sentence. Choose answers from the box. The current through an ohmic conductor is directly proportional to. Okay, now this is an Ohm's law question, so you need to learn that the current is directly proportional to the potential difference, and that all relies upon the temperature remaining constant, provided that the temperature remains constant. Figure 7 shows a current potential difference graph for a filament lamp. Explain how the resistance of a filament lamp changes as the potential difference across it increases. So effectively, as the potential difference increases, you find that the current increases, and what that does is it causes those positive metal ions within that metal wire to vibrate more, and that inhibits the flow of electrons through it, and that's all due to the temperature increasing. So as potential difference increases, the current increases, as does the temperature. This causes the metal ions to vibrate more and inhibits the flow of electrons. As a result, resistance increases. 5.3. Many householders are replacing their filament lamps with LED lamps, which are more energy efficient. What does more energy efficient mean? So remember, efficiency is given by the equation useful energy out over total energy in. And so effectively, if you increase the efficiency, it means that a higher percentage of the power is transferred usefully. A light-dependent resistor, LDR, is used to turn on an outside lamp when it gets dark. Part of the circuit is shown in figure 8. Okay, so here's our battery again. Here's a regular resistor. And here's your LDR. The light intensity decreases. Okay, just remember for me that when light intensity decreases, the LDR's resistance increases. So what happens to the potential difference across the LDR and the current in the LDR? So this becomes very important now, because when resistance increases, the potential difference increases and the current decreases. So that's something you need to remember, the pattern. So potential difference increases and the current decreases. What is the resistance of the LDR when the potential difference across it is 4 volts? Give a reason for your answer. So the crucial thing here is that this LDR has a voltage of 4 volts. Now remember, in a series circuit, as we have here, that voltage is shared between the components. So if the total voltage of the battery is 12 volts, it means that this resistor up here must have a voltage of 8 volts, because 8 plus 4 is 12. So if we compare those potential differences, we can see that it's twice as big for the regular resistor, which means that the resistance of the 4 volt LDR must be half of that, which is 1000 ohms. And the reason for this is that the potential difference is shared between the components in proportion to the resistance. Calculate the current through the LDR when the resistance of the LDR is 5,000 ohms and give your answer to two significant figures. So in order to answer this question, we need to remember a few circuit rules. Now, this is a series circuit, and what that means is that the current is the same everywhere. So we know that the voltage is 12 volts. We've been given the resistance of this resistor as being 2,000 ohms. And if we look at the question, the other resistor is 5,000 ohms, making the total resistance of this circuit 7,000 ohms. So we know the resistance is 7,000, we know the potential difference of voltage is 12 volts, so we're after current, which is current is potential difference divided by resistance. So the voltage was 12 volts, the resistance was 7,000. And you'll get a value which is 0.001714, and then to 2 sig fig, just 0017. 6. Smoke alarms contain an alpha radiation source and a radiation detector. Figure 9 shows parts of the inside of a smoke alarm. So you have an alpha radiation source, and then there's a radiation detector, and then the smoke particles go between the two. The smoke alarm stays off while alpha radiation reaches the detector. Why does the alarm switch on when the smoke particles enter the plastic casing? And this is all to do with penetrating powers. Remember that alpha is stopped by just a few centimetres of air. So the fact that there's smoke particles there means that they will stop the alpha reaching the detector. Why is it safe to use a source of alpha radiation in a house? And I've already alluded to this. It's because alpha radiation is not very penetrating, so it won't actually reach you. The smoke alarm would not work with a radiation source that emits beta or gamma radiation. Explain why. So it's all the same question really. So we know that that radiation is supposed to go from here to here, and beta and gamma are both extremely penetrating. Beta is only stopped by aluminium foil, gamma is stopped by lead or by concrete, so the smoke would not be enough to stop that gamma or beta radiation. So we need to say beta and gamma radiation would penetrate the smoke. And if we have another look, so we have a radiation detector, so effectively there'd be no change in the count rate detected by that radiation detector. Figure 10 shows how the count rate detected from the radiation source in the smoke alarm changes with time. The smoke alarm switches on when the count rate falls to 80 counts per second. Explain why the radiation source inside the smoke alarm should have a long half-life. This is quite an annoying question because annoyingly they won't accept the answer, which would be so you don't have to replace the source within the smoke detector. I don't know why, that seems a very valid reason. So actually what we have to do is actually look at what the graph is telling us. So let's have a look first of all at 80 counts per second. That time in half-lives would be 1.3 half-lives. So let's just make a really bland comment. So until 1.3 half-lives have taken place, the count rate is above 80 per second. And then let's have a look at why it should be a long half-life. And that means that for a large amount of time that the amount of radiation or the count rate remains fairly stable. Figure 11 shows a patient who has been injected with a radioactive source for medical diagnosis, radiation detector. Explain the ideal properties of a radioactive source for use in medical diagnosis. 4 marks, so we want to make 4 separate points. First of all, the radioactive source should emit gamma radiation because it is the least ionizing and therefore the least dangerous when found within the body. It's also the most penetrating, which is good because it means it will get through skin and bone. In terms of half-life, you want it to be long enough so you can actually detect the gamma radiation, but not so long that it's held within the body for a long time, because obviously that could lead to mutation and cancer. So a suitable half-life, which is only a few hours, to prevent mutation of cells, which could cause cancer. Seven, a student investigated how the pressure exerted by a gas varies with the volume of the gas. Figure 12 shows the equipment the student used. A pump was used to compress the gas in a tube. As the volume of the gas decreases, the pressure of the gas increases. The student only recorded 1 set of results. Give 2 reasons why taking repeat readings could provide accurate data. This is quite a frustrating question. It's probably worth learning this from an experimental point of view. Taking repeat readings allows you to take an average, and it also enables you to discount anomalous results. Because if you've only got 1 reading, how can you spot if it's not right or if it doesn't fit the trend? No, I've spelled that wrong. I hate spelling things wrong. Figure 13 shows the position of the student's eye when taking volume measurements. So look, they're being good, they're level with the meniscus. Explain what type of error would be caused if the student's eye was not in line with the level of the liquid in the tube. Now this would be random error, because the student's eye position would not be at the same level each time. If the gas is compressed too quickly, the temperature of the gas increases. Explain how the temperature increase would affect the pressure exerted by the gas. So effectively, these gas particles gain kinetic energy, which means they collide with the walls of the container with greater force and generates higher pressure. So as temperature increases, the pressure increases. Because the gas particles gain kinetic energy. One of the students' results is given below. The pressure and the volume. Calculate the volume of the gas when the pressure was 1.8 times 10 to the 5 Pa. The temperature of the gas was constant. So this is pressure 1, this is volume 1, this is pressure 2. We're after volume 2, so we need P1V1 equals P2V2, so that's 1.6 times 10 to the 5 times 9 equals 1.8 times 10 to the 5 times x, and then when you've done 1.6 times 10 to the 5 times 9, you get 1.4 1.44 times 10 to the 6 equals 1.8 times 10 to the 5x. So to get x by itself, you divide both sides by 1.8 times 10 to the 5 to get x equals 8. 7.5. Figure 14 shows a person using a bicycle pump to inflate a tyre. The internal energy of the air increases as the tyre is inflated. Explain why. Now remember that the internal energy is the total of both the kinetic energy and the potential energy of the particles in the object. So effectively, as you inflate the tyre, then the kinetic energy of the air particles increases, and as such their temperature increases. The second marking point is less obvious, and you need to state that work is done on the air in the tyre. Nuclear power stations generate electricity through nuclear fission. Electricity can also be generated by burning shale gas. Shale gas is natural gas trapped in rocks. Shale gas can be extracted by a process called fracking. There is some evidence that fracking causes minor earthquakes, that's bad. Burning shale gas adds CO2 to the atmosphere. Describe the advantages of nuclear power compared with the use of shale gas to generate electricity. So let's first of all point out the 2 points they've given us for free. So you want to state that nuclear power does not release carbon dioxide and therefore does not contribute to global warming, because remember, carbon dioxide is a greenhouse gas. Also state that nuclear power does not cause earthquakes. And then from your own knowledge, hopefully you know that nuclear power is a very concentrated source of energy. So nuclear power releases more energy per kilogram. What is the name of one fuel used in nuclear power stations? So the most obvious one for me is uranium-235. I don't think you need the mass number. But you could have also said plutonium. Describe the process of nuclear fission. So let's start by defining it. So a neutron is absorbed by the nuclei of an atom. The nuclei splits to form two smaller daughter nuclei and 3 neutrons are released. So if we were to take a little picture, here's our neutron colliding with that parent nuclei, which splits into 2 smaller daughter nuclei, and 2 to 3 neutrons are released. And remember, if they go and collide with more nuclei, then a chain reaction can be set up. 9. Figure 15 shows a coffee machine. The coffee machine uses an electric element to heat the water. The coffee machine has a metal case. Why would it be dangerous for the live wire of the electric cable to touch the metal case? Well, mainly because there'd be a huge risk of electrocution if you were to touch it, because the excess charge would try and drain away through you. The power output of the coffee machine is 2.53 kilowatts. The mains potential difference is 230 volts. Calculate the current in the coffee machine. So we need PIV, which states that current is power divided by potential difference. Our power is 2.53, which we need to multiply by 1,000 to get it into watts. Then divide by 230. And then when you pop that into your calculator, you get a value which is 11 amps. The coffee machine heats water from 20 degrees to 90 degrees. The power output of the coffee machine is 2.53 kilowatts. The specific heat capacity of water is 4,200 J per kJ. degrees Celsius. Calculate the mass of water that the coffee machine can heat in 14 seconds. Okay, this is quite a hard one because we definitely need this equation, Q equals mc delta T. Energy equals mass times specific heat capacity times change in temperature. However, we're after the mass, but we don't know the energy, Q, so we need an equation linking those, which is this formula triangle, which states that energy equals power times time. So let's do that first of all. So we need to convert again to watts by timesing by 1,000, and then time is just 14 seconds. So when you pop that into your calculator, you'll get an energy value which is 35,420 joules. So now we're ready to use Q equals mc delta T. So we've just worked out Q. We're after M. The specific heat capacity we've been told is 4,200. The temperature change up here is 70 degrees. So sort out your right hand side by doing 4,200 times 70 to get this number here, 294,000. And then to get M, you want to divide both sides by 294,000 and you'll get a value which is 0.12 kilograms. 10. Figure 16 shows a wind turbine. At a particular wind speed, a volume of 2.3 times 10 to the 4 meters cubed of air passes the blades each second. The density of the air is 1.2 kg per meters cubed. Calculate the mass of air passing the blades per second. I use drunk men vomit here. So mass is density times volume. Our density is 1.2. Our volume is 2.3 times 10 to the 4. Just put that into your calculator as it stands. You'll get a value which is 2.76 times 10 to the 4. You can keep that in standard form or convert it to an ordinary number. The power output of the turbine is directly proportional to the kinetic energy of the air passing the blades each second. Describe the effect on the power output when the wind speed is halved. Okay, first of all, I want to say that this question is absolutely ridiculous. I've got no clue what it's doing on a GCSE Physics paper, but I'm going to talk you through how you go about it. So let's consider if we halve the wind speed, then what you're doing is halving the mass of air that passes the turbine in a given time frame. So I'm going to start by writing that. Now consider which equation we're looking at. So kinetic energy is half mv squared. So as kinetic energy equals half mv squared, if we halve the speed and therefore halve the mass, then we reduce that kinetic energy by a factor of 2. And so if we've reduced the kinetic energy by a factor of 2, now we need to consider what would happen to V. And notice, because it's squared, rather than that being reduced by 2, it would be reduced by a factor of 4. I don't know how you're supposed to fit this all in. So our final point is to say that the total effect on kinetic energy is to reduce it by a factor of 8, which is, I'm sorry, crazy, but thank goodness it's not worth like 8 marks. At a different wind speed, the wind turbine has a power of 388 kilowatts. The mass of air passing the wind turbine each second is 13,800 kilograms. Calculate the speed of the air passing the blades each second and assume that the process is 100% efficient. So we have a mass value here, power, we're after speed. So in order to do this, and we also have time here, we need KE equals half mv squared, because that's the only value we can use here that contains speed. However, we don't have enough information for that. We need to find the energy, which is why we need this one. So energy equals power times time. The power is 388 kilowatts, which we times by 1,000 to convert into watts, and then times by the time, which is just 1 second. So there we have our KE equals half of the mass, which we've been told is 13,800, and then we're after speed, so I'm going to keep that as v squared. So if we halve 13,800, we get 6,900 v squared. To get v by itself, we need to divide both sides by 6,900 to get 56.231 equals v squared, and then to get v by itself, we need to square root both sides, and therefore v equals 7.50 meters per second. So an awful lot of working for that last question.